do something a bit simpler. Let me have a look. New share. So I'll just share the whole desktop. I was trying to just share one window, and I guess that was a bit ambitious. Can you see that, guys?
There we go. That's perfect.
Perfect.
That looks like a presentation.
I'll take that. Great. Okay. Right, guys. Well, thank you very much for the invite to speak. It's a real privilege for me to be part of this community. I'm presenting as an academic from the University of Leeds. My name is Dr. Andy Young. I'm a fluid mechanics guy. I've been involved in liquid cooling in various ways over the years, over the past sort of 10 to 15 years. I'm going to talk to you today about the journey that the heat takes from micro scale of the chips through to the facility, and the reasons for why standardization is a challenge for advanced cooling solutions. So there's an interactive whiteboard, Etherpad, which we can use to communicate, and hopefully we'll have some time if there's any questions or chat that people want to have. But please do use the facilities provided if you can, and hopefully I'll enable us to have some time to discuss some of these broader points. Okay, so micro to macro, chip to solution to facility, a journey on the back of heat. So generally speaking, air cooling lends itself to standardization. And why is that? Well, air could be seen as a cooling reservoir of heat, and the air cooling solutions are weakly coupled generally to the IT platform. And not to say that one heatsink will do them all, but the job of standardization for air cooling systems is somewhat simplified due to that weak coupling. And also air inlets set boundary conditions of flow and temperature to the cooling solutions too. So these things together combine to make the business of standardization more straightforward, where local performance is independent of the wider system. When we look at liquid cooling solutions, we find a different picture. So the same 3 points, but sort of the antidote to those really is that there's the IT platform's more integrated with the cooling solution. Think of immersion cooling, for example, but also closely coupled cold plates, more close coupling, no buffer between them, physical contact, physical immersion. Liquids involved, multiple in many cases, and flow in intersecting loops. So therefore the performance is dependent on the wider facility, and the intersection means that there is feedback, the outflow from one being the inflow to the other. So interdependency and feedback occurs in advanced liquid cooling solutions. So for this reason, standardization is challenging. Not to say we can't do something about it. So as you can see, there's the now familiar image where we see the various fluid loops with heat exchangers marking their intersection, those grey boxes, and the performance in those boxes, those heat exchangers, depends on the fluid type and the flow on either side. And while the efficacy of those heat exchangers is standardized for the CDUs due to them being based on mature technology, it's just a heat exchanger in a box. We understand them well. The same cannot be said necessarily for the heat transfer from the IT, which is more dependent on the particular cooling solution and the IT SKU that's applied. So interdependency and feedback occurs at the interface of the loops and the intersections. Some of those are simple and well understood, mature technologies, but when we look at these cooling solutions, we see a great variety and a great degree of dependency on the efficacy of the heat exchanger that occurs close to the heat source, where the thermal control is most important. So I didn't click through the slides while I was talking, my bad. I'll try and click a bit more in sync. Okay, so hopefully you get the kind of main theme there. So unlike sizing a heat exchanger, there is a high degree of variability across the different advanced cooling solution types, where the IT can be seen and has been said to be an integrated appliance, where the cooling solution and the IT are tightly integrated and need to be designed together in many ways. And adaptation and configuration of the advanced cooling solution may be required to suit a particular SKU. And as you know, different SKUs and different layouts of heat sources occurs on an almost daily basis. Maybe not quite daily, but certainly very regularly. And we need to come up with a system of standardization that can reflect those changes, embrace that, but also give some stability, at least in terms of the methodology that we're taking to understand what's going on. So the driving factors for standardization are well known within the industry, of course, but the main one is to achieve something that Wolf mentioned a few moments ago around the integration of the advanced cooling solution with the facilities cooling system, and together enable the engineers and the operators to achieve the main goals of minimization of the operating pressure, the case temperatures, and the energy expenditure, all those things that we need to work together to achieve. How that is arrived at, in my view, is really from understanding things at a fairly granular level, thus the micro focus that we're taking here, where we account for and accumulate the pressure drop and the temperature rise, the power penalty for pumping and fans, and the air side losses that need to be handled, as a burden to the parallel air cooling system. So this needs to be accumulated in each loop and across each intersection of the system, wherever we find it. So really, we're going to take a bit of a whistle-stop tour through the system now that we've got some orientation and understand the journey that the heat takes at each of the steps. And so you can see my little cartoon has some fun with this. So by going from chip through cooling solutions to facility, we're basically moving down the temperature gradient. So that little orange car, J is for joule, the symbol for heat, at least in the Europe, or at least in the UK. And we're going to kind of really take a tour in those 3 steps through the different ways in which the coolant flow rate and choices of IT affect what's happening, and how we can possibly tie this together into some sort of standardization. Okay, so starting off with the chip then. So as you know, there's a whole variety of different form factors, SKUs. Increasingly, we're finding multiple heat sources, and more of those are not just along for the ride, but are providing a minor proportion of heat, but in many cases are starting to be significant in their contribution to heat, and also significant in terms of the need to control the temperature carefully. So it's not just one heat source, but multiple heat sources. What's going on underneath the heat spreader is often as important as what's going on above it. And whilst this is proprietary to the supplier of the ITE, their insight to what the thermal performance of the integrated heat spreader and the TIM and the heat sources below that need to be brought into the scope of consideration, due to the close coupling that we have in liquid cooling systems. So there's a wide range of form factors and SKUs. They're changing all the time, they're highly complex, and they're highly varied. So if we were to take a chip, for example, and I've brought in a few images from Intel, so hopefully they don't mind, they're all in the public domain, these images. But so if we take a chip, you can see in green, we find the multiple heat sources. Each of those has got a critical temperature that must be carefully controlled. The dependency of that on the local ambient is through thermal resistances, which depend on convection and conduction. And for air cooling systems at least, then there's proprietary data published on the air cooling solutions that relate the thermal resistance for each of the SKUs and the matching heat sinks to the flow rates. We don't yet have this, of course, for the more general advanced cooling solutions. But there's no reason, if we understand the cues that come together to provide data for the thermal resistance, why we could not produce it. But we need to be careful how we apply that, of course. So, yeah, so we find, therefore, if we sort of dig into what the thermal resistance depends on above and below the integrated heat spreader, we can unpack the physics and really understand how we can represent it for any cooling system. So taking the heat spreader, the first contribution is just one-dimensional conductivity. That depends on the thickness and the material properties which are present in the stack up of material. And the heat just travels in a one-dimensional way. It's quite simple through the material. No biggie, no confusion or mystery to that. But there's not only one mode of heat transfer due to conduction that we need to consider. As you probably know, there is a lateral spreading of heat from the heat sources to make use of most of the width of the heat sink base as we possibly can have. And that, particularly when you have multiple heat sources, becomes a very significant contribution to the overall thermal resistance. It depends on all the same factors as 1D conduction. But also depends on the distribution of the heat sources. And bear in mind, we've now got multiple heat sources, each of them are important, then these effects can become quite a dominant consideration of thermal design. It depends on the layer up of materials and the order in which they're stacked. And it also, and quite surprisingly, it depends on the convection thermal resistance above it. So this is the first example of coupling between different levels of cooling at different scales. So convection cooling, which you might think has been independent of conduction, feeds back and affects the thermal spreading resistance. So whilst the heat is spreading out, enjoying more area, it doesn't enjoy all of the heat sink. And you can couple these things together if you take a systems approach to analysis. So in summary, for the chip at least, we find a lot of complexity, particularly with the heat spreading resistances, which are key for multiple heat sources for modern SKUs. It's coupled to convection, which is surprising, but a real effect. And therefore, a change to the SKU is going to significantly affect the cooling solution requirements, even at the chip scale. So there's a big sort of a big message there that we need to take on board. Second up, if we start moving down that curve in our little orange car towards the cooling solution, we can now look above the sort of heat sink and the fluid region above it, be that air or liquid. And this is where we can focus on the convection cooling that is coupled, as we said, to the conduction cooling. So we have a local ambient temperature that's supplied by the facility, but that isn't what the heatsink or the cold plate experiences. It's there's a system ambient that's supplied by the facility, and there's a local ambient which is experienced by the cooling solution. The difference between those two depends on the preheating effects of any heat that is upstream. Now, as we said before, the heating in advanced cooling solutions occurs in loops. So any upstream cold plates or equipment provides a preheat. That might be across the scale of a chassis, or maybe within on a server board. So the interference upstream of significant heat sources can have quite a large effect. And if you change the flow rate, then the degree of that effect is going to change. So right away, we're seeing a precursor effect due to upstream heat sources, which is going to mean that the temperature reference point of one chip is going to be different from another. A great example of a systems effect. Also, looking at the heatsink, we know that the thermal resistance between the heatsink base and the fluid depends on the surface area of all the fins, but it also depends very critically on the flow rate of the coolant and its properties that depend on the inlet temperature. And the main cue here is to maximize the difference in temperature between the heatsink and the fluid, from inlet to outlet, and also from root to the fins. Change the flow rate, change the heat spreading resistance, recruit more fins into the heat transfer package, change the fin design, you're going to see a big change in the performance. Imagine for immersion cooling, where you've got natural buoyancy causing the flow to move through the heatsink. The fluid has to decide, based on the balance of forces, if it's going to bypass or flow through that particular heatsink. More heat means more momentum added to the fluid, but these things are coupled. The heat transfer performance determines the buoyancy force that in turn determines the cooling. So all these things are coupled together in a complex way and can be packaged into this thing called effectiveness. And effectiveness is a common tool that's used in heat exchanger design, and the same tool exists for heat sinks and liquid cooling solutions. Therefore, one proposal might be to think of the heatsink as a heat exchanger, use effectiveness, but represent and unpack how all these dependencies stack together. So in doing so, it is possible to construct data just like that supplied by Intel for the air cooling solutions, for any of the liquid cooling solutions out there. An example here is shown for a cold plate, but you can do this for any, be that forced or natural convection. And that the dependency can be measured, and sensitivity, so this can be done to see which are major, which are minor. So we can start to understand this, but clearly there is significant feedback between convection cooling and the efficacy of the cooling solution. Initially, we said about the spreading resistance. Clearly, the heatsink performance is going to be very affected by the flow rate, and therefore, again, changing the IT SKU, changing the fluid and the flow rate is going to have a big effect on the cooling solution requirements. So moving on to look at the facility scale now, we can see this most clearly by example. So if you take a look at a rear door heat exchanger, a cold plate, or an immersion cooling solution, and consider the way the system ambient is changed, and consider the ways in which feedback occurs as we look at this on a systems scale. So initially, for a rear door heat exchanger, we have a CPU being cooled by our familiar friend, that air heatsink. And essentially, rear door heat exchange is an air cooling solution. We're just using liquids to integrate the heat and dissipate it in a controlled manner outside of the sort of bulk environment of the data hall. So we have, as we said before, weakly coupled thermal solution to the IT platform. The inlet boundary conditions are set. So irrespective of what's happening downstream, that system ambient temperature is fixed. And the local performance of that heatsink is really determined by those boundary conditions that we spoke about, which are, in a sense, protected or guaranteed or assured by the control system that drives the HVAC equipment. So in that way, you can see how the upstream system ambient conditions are set, and it doesn't really have that strong effect on the performance of the system downstream. So we have a weak coupling. We have stable boundary conditions set, and also the HVAC equipment can compensate for the airside radiant heat losses as well. So this is a good system in terms of its stability, but of course we all know that getting a gas involved in heat exchange is not going to give you a great deal of performance, and we still have to maintain the temperature of a bulk environment with all the fabric losses and all the additional energy costs that are associated with that. So moving on then to look at the same system, but replacing it with the CPU with the GPU, we have a change to the cooling solution. There's a different heat sink involved, therefore we've got different spreading due to multiple heat sources, and we've got a different convection resistance due to a far bigger heat sink. But still we can set the boundary conditions for the flow and temperature. Although we have a marked increase in the heat load on the system, which has an impact on the duty of the Viridor heat exchanger and the heat exchangers downstream, we still have control over our environment. We still have local performance that's independent of the wider facility. So for Viridor heat exchangers of these various types, yes, we have to have good control and appropriate duty of the heat dissipation equipment. And if we put too much burden on the HVAC equipment to make up the difference, then that's going to affect our PUE. But essentially the system is well behaved, and therefore standardization is fairly straightforward. In comparison, looking at cold plates now, it's a different picture. So now the air heat dissipation route is there in parallel, and we get feedback. So you can see this by having a tightly integrated cooling solution. So the spreading and thermal resistance due to convection are closely coupled to the IT platform SKU. We have a feedback loop, so the flow rate through the cold plate is the same flow rate through the CDU heat exchanger. And if we change that flow rate, then it's going to affect the thermal resistance of the CDU. And that in turn is going to affect the temperature of the return to the cold plate, and therefore the system ambient of the temperature of the fluid as it approaches the cold plate in that loop. So due to that loop, due to the dependency of the heat exchanger and the CDU on both sides of the hot and cold side flow rates, we have a feedback loop, and the flow temperature is affected by the flow rate, and therefore we have not instability as such, but we have a dependency that we have to consider, linking the facility to the cooling solution. So therefore, if we change the flow rate, we can see very strong effects on the case temperature, and therefore we need to consider that when we're developing the whole system. Similarly, for immersion cooling, again, we can see that we have a very different cooling mechanism based on natural convection. We only have one fluid in the loop now. The facility coolant, we've lost CDU, which is going to boost performance by a few degrees, which is going to have a big effect on energy efficiency. But of course, with it being, as I said before, natural convection, there's inherent coupling between the cooling and the flow rate of that coolant in the immersion zone. So those thermal resistances are very dependent on the efficacy of the overall cooling system. And we have the same feedback loop happening, whereby the flow rate of the cooling water is affecting the overall thermal resistance of the heat exchanger, and therefore affecting the return temperature, and so therefore the case temperature of the processors. So at the facilities scale, you can see, hopefully those illustrations have helped to show how the flow rate needed to achieve thermal resistance targets has a knock-on effect, not only at the heatsink scale local to the processor, it also has an effect on the heat exchanger, and therefore feeds back and affects the temperature across the whole system. And that's the end of the journey that we've taken. So in conclusion, different SKUs and different cooling solution selections can significantly influence the requirements and performance across all scales. You have to take a systems approach to design, and this obviously is going to affect the system control and monitoring too. But by standardization and by understanding, maybe using some of the approaches proposed here, we can work towards having a mature standardization approach as the advanced cooling solutions themselves mature as a technology. A call to action to get involved, of course, unless you are not already. So there's groups existing in OCS for advanced cooling solutions and for each of the cooling solution types which I've shown you today. So please do get involved. Thanks very much, guys. All the best, and hopefully you've got some time for questions.
Thanks, Andy. I thought that was a brilliant session. I love how you compared heat sinks with heat exchangers. I think you're completely right in making that comparison, and it shows how the industry is shifting, right?
Mm-hmm. That's great.
So do we have any questions from the community?
I just want to say this is pretty great presentation.
Oh, that's very kind. Thank you very much.
And just a reminder to everyone watching, if you do have any questions for Andy or any of our speakers, you can click the join speaker access button to be admitted into the Zoom call to ask those questions in person. Or feel free to do that via the chat as well.
And of course, you can use the virtual notepad underneath the presentation, right?
Yes.
Okay, so thanks again to everybody, and good luck.